Oh, this just has a slide. It doesn't have the picture, but here we are in the room. I have to show you my shirt.
Yes.
Astronomy rocks. So there's this funny thing that people give me shirts. I always wear them. This was a gift from some of my TAs, basically. Good. This because of what I'm doing here. All right, so today we're going to talk about asteroid occultations at Westport here and other nearby places. And this is, I don't know when the last time it was that I talked about this. It's 2-3 years, 3-4 years ago. Yeah, it's been a while. A few things have happened in terms of the development of the field and what we've been able to do here. This talk's going to be a collaboration between me and 4 of the students who are helping with the occultations. They're doing most of the hard work, like staying up at 3 in the morning. And I should mention Bob too, because Bob used to do these. I don't know. I guess he
wisened up.
He wised up. Yeah.
One of these days.
Yeah.
Sometimes I go up there and wait pom-poms.
And you're really good at that. Okay, so they will be coming up and talking about or certain parts of this lecture at different places. I'm going to first talk about asteroids just to refresh all your memories about where they are and such, and then we've divided the lecture up, and so it'll be a nice little tag team type of thing. Now, the other thing I should point out is that they did their own slides, which is good. It's a little different than what I've done, but it'll cause maybe some confusion as we switch between, but that's all right. So this is just a picture of asteroid Ida, and there's a little tiny moon there on the right, and this was seen by a spacecraft a few years ago now. And the best way to understand asteroids is to actually go to the asteroid and take pictures of it. But in lieu of that, what's the other best way? And the answer is occultations. So just to remind you of the asteroids, most of the asteroids are in the main, what's called the main belt. Most of the known asteroids are in what's called the main belt between Mars and Jupiter. That would be the white dots on the screen there. There are also asteroids that move in coincidence with Jupiter, and those are called the Trojans. And there's 3 groups of those. There's the Trojans, which I think are behind, the Greeks, which are ahead, and then there's the Hildas, which are on the other side. So these are what was known to be most of the asteroids up until about 30 years ago, when more were discovered beyond Neptune. Besides Pluto, because we thought Pluto was a planet, it actually is one of the objects in the area. The other thing I want to point out is there are asteroids that go pass by the Earth. These are the near-Earth asteroids. And this is just a graph. It's updated daily at JPL. So as of tonight, there are 37,000 potentially hazardous asteroids. I hope that makes y'all feel good.
Nothing to see here, folks. Move on.
That's actually not quite true. It's really these bigger ones that you're after. A lot of these are smaller ones that are, they should say Earth crossing asteroids. I think it's near Earth asteroids. That's what it says. So I've lied here in the plot. It's not potential. Many are potentially hazardous, but most of these are just near Earth asteroids. Most of them are small and not a big deal. But if you get above, say, 100 meters or so, you could take out a city. And if you get bigger than that, it could be a little worse than that. So, and most of the 1 kilometer ones are actually, we think we found most of those. Just don't look up, I guess. And we're working on the ones that are sub-kilometer, and most of the recent ones are actually kind of small, and the things that make the fireballs that you see. So if you go beyond Jupiter, so now you see right in the center here, there's Jupiter and Saturn, and then the inner planets are inside that that yellow disk inside, and you can see the Trojans are kind of this gray blob in this plot. If you go beyond that, the green ones are asteroids between Neptune and Jupiter. All of those are actually not stable in their orbits. They're at one point or another are going to interact with one of the planets and either be kicked in or kicked out of that area. And a lifetime of a few million years, if I'm not mistaken. So, and then beyond Neptune are what we now call the trans-Neptunian objects, or TNOs. These are primarily Kuiper. It's another asteroid belt that is beyond Neptune. And we only see the bigger ones in that set because that's all we can see at the moment, just from the light coming off it. And so that's another asteroid belt. There's postulated a third asteroid belt, even further out, but there's no really good evidence.
Is that beyond the Oort cloud or?
Beyond, no, that's a good question. I think it would probably be at the edge of the Oort cloud. That would not be the Oort cloud. The Oort cloud being where most of the comets are supposed to be located. And then beyond the TNOs are distant objects. Well, a few of those, Sedna's the most famous. These are all discovered in the 90s and the knots. These three, I believe, well, you can see where they are. 2012 was this one. 2015 was that one. Sedna was earlier. And this is the orbits of these are such that these are the ones that are the best evidence for potential planet 9, how these orbits tend to line up. And planet 9 would be going through those at a certain angle. So those are the asteroids. Just one more plot, especially with the distance ones. I want to give you a sense of the distances. This is a plot, and I almost didn't put this in, but I thought I'd just try. On the lower axis, the horizontal axis, is the distance from the sun in astronomical units. 1 astronomical unit is the distance from the Earth to the sun, which is 93 million miles. And we're starting here at 30. And so we're starting basically at Neptune. Pluto is one of these purple dots here, somewhere in this region. This is the Kuiper belt. The lower left band there is the Kuiper belt. And then there's a bunch of scattered objects or different portions of this space. What is this? What is the vertical axis? I didn't tell you what that is. That's the eccentricity. What's the eccentricity? The eccentricity is how elliptical the orbit is. So zero eccentricity would be a circular orbit. And then as you stretch that out, you get more elliptical and elliptical. And 1 would be where it's basically parabolic, just be an ellipse with an infinite radius, I suppose is the way to say it. So the bigger the eccentricity, the more elliptical the orbit is. Think comets for the higher numbers. And those three distant objects are over way up here in the upper right of this, the 3 objects that I showed you the orbits of on the previous slide. But there are other things scattered, extremely detached. There's all sorts of different names. It's an unexplored territory. I just want to point one of these out, which is 2004 XR 190 down there, which is beyond the Kuiper belt. We've actually observed an occultation of that one here at Westport. I'll show you that in a bit. Okay, so this is where I'm going to get the students to come up and discuss what they've been doing.
Mention one other thing.
Yes.
You had on your slide, you're showing the main asteroid belt, and there's all these white dots all over the place.
Yes.
And I just want to point out that as dense as that looks, the average distance between them is 600 million.
Yeah,
miles.
it looks pretty awful there, doesn't it? But yeah, you wouldn't know it. So you go to if you go back to the first Star Wars, which is actually episode 4. I've never understood that, but there's this great thing through an asteroid belt. That's a really dense asteroid belt in that movie. Yes,
Yeah, that would be a planet in a hurry.
that would, yes,
Right.
yes. All right. Okay, so first up is Monica. She's going to tell us what is an occultation, which is how we measure these things. And I got to put you over to there, and I'm going to let you go from there.
Hello, everyone.
Hello.
Thank you. I was actually the OG, besides Serena. I was the first one to do this research with Kevin. I've been doing it for a little over a year, which is way too long. And I'm actually graduating soon, high school, and leaving, fleeing the nest for college. So this was a really great opportunity for me to learn a little bit about scientific research, but I'm very pleased to talk to you today about occultations, and most specifically, what even is an asteroid occultation. So you can really think of an asteroid occultation as basically an eclipse, except it's an asteroid and a nearby star, nearby meaning pretty far, but as far as stars go, it's pretty close by. And so like an eclipse, when the asteroid crosses in front of the star, the starlight dips and the asteroid casts a shadow here on Earth, which I have represented with this image here. So these blue lines represent where we really think the asteroid shadow is going to be, but these red lines here are the error margins. So the shadow can be really anywhere from across these lines. Now, like, why even research occultations? I ask myself that every day. There are many things that occultations or an asteroid occultations tell us. The location of the shadow can help us predict the orbit of the asteroid. And by us, I don't mean actually us here at Westport. Our data helps to tell the orbit and the asteroid shape and size. So the shadow, depending on how big it is, and where we see the shadow here on Earth, which is what our occultations are for, can help us tell what kind of shape and size the asteroid has. So one photo I picked up right here, which is actually really cool. It used, I believe, Serena, Kevin, and ours data. I forget exactly which occultation this is, but you can see our names right here. And here, our data was used to actually help render a 3D model of an asteroid, which is pretty cool. So you can predict orbit, shape, and size of asteroid using these occultations. And a little bit more in depth, when the asteroid casts a shadow on Earth, it's best to have multiple locations, because that can help, that gives us a better understanding about all these things about the asteroid. And that kind of makes sense. So like, for example, for this image here, we only had one location, one station, which doesn't give us a lot of data. But something like this here, for example, we have a location right at the edge here. If this location does observe the occultation, then we know that the shadow is somewhere up here and different from what we had originally predicted. And also these two locations here help as well. This is, you can see, this is the green line. This is where we think the shadow is going to be. And again, if these locations say, yes, the shadow was here, we observed the occultation, it again helps us narrow down exactly all these metrics about the asteroid. So, but like, what exactly is our research? How do we do this? So we kind of have two steps. We have a portion where we come out to Westport or wherever location we are, and we manually record the occultation. We, here at Westport, since I'm most familiar with how we do it here at Westport, we use the 14-inch Celestron in the dome. We attach a camera to it, and it has a bunch of cords, but most importantly, a GPS. And then we use a program called SharpCat, which you can see right here, to record the occultation. Once we have the recordings, we come together and we mark.
Now that's new.
So this would be, we use computer programming to analyze these recordings, and we end up with a light curve. which is seen here. So then we take this light curve right here. You can see this is where the occultation is, or this is where the starlight dips. And we isolate that with computer programming, which you can see Kevin pointing to here. So what's that painting called? It's like one of those moments. Look how happy he
Yeah,
looks.
it's a Michael.
Look how happy he looks. Occultations are great. Just wow. So, and finally, so side note, we have analysis parties, which are actually quite fun sometimes. When we all come together and we analyze our data, it can be an excruciating process. But it could also be fun. This day, I had brought a cauldron of candy. Kevin was not happy about that because he ate all the Twizzlers. But you know, we had fun. We had fun. But finally, once we've isolated where the starlight dips, we take that data, we send it off to Norm, which I have an email here. I don't know who Norm is. I don't know what he does. I'm assuming Norm then takes the data and sends it to JPL, but he's sort of this mysterious man that I have never really met. So I'm assuming he sends that data to JPL. And then we have our data. Our data is then reviewed. It takes a long time. It takes way long. I've been doing this research for like over a year, and I think we only have, or at least I only have 7 reports that have been reviewed and sent to JPL because it takes a long time. But once everything is reviewed, our data is used kind of like this. So these dots right here are the predicted, what astronomers had predicted the path of the asteroid was going to be. But this is what the path of the asteroid was based on our observations, which again, not lying, you can see our name right here. But yeah, then you have predicted versus observed, and then science. So yeah, but that's pretty much it for what occultations are. Does anyone have any questions if I explained something?
Sure, yeah. So Monica, like if you don't see something, let's science.
Yeah.
How often do you come
absolutely.
up here and you're skunked and
Yeah.
nothing happens?
Oh, it's like, I would say 9 out of 10. It's pretty bad. And there definitely have been some times when we were supposed to see the event and we didn't. And so we reported it because those misses are very important for astronomers to use to recalculate things. So yes, in science, a miss is just as important as a hit.
What's the best occultation you have seen?
Gosh, I can't name them off the top of my head because a lot of times they're just numbers. That doesn't really stay in my head. There have been a couple of really good occultations where when we're looking at the recording, if I go back a bit, this far image all the way to the right, that's what we see up in the dome. And there have been times where we've actually seen the star just like, bloop, bloop, like come out of his existence and come right back into existence, which is something really cool to witness. It's like a blink of existence. But most times it's so dark and we can't really see anything. So we just set it up and then we wait in the cold for like 15 minutes and then we take it all down.
How long do they last?
They can last, some of them can be really long. We've had ones that are like 10 seconds. Those are generally considered to be pretty long. And then we have ones that are like half of a second, if not shorter. So they can range. Yeah.
But you also had some occultations where the predicted chances of seeing it are like 5% or something, and you still get it.
I would say it's probably the other way around.
He has had some like that where he's got 2% chance and he gets it.
The very rare,
Yeah.
very, very rare.
Yes.
Explain why you use a GPS. What's the reason for that?
So the GPS helps us when we go back and analyze our recordings. Each frame needs to be associated with like a timestamp. And that way, because like also these asteroid occultations based on our predictions are supposed to occur at a very specific time. And so the GPS helps let us know that it helps make our information statistically significant. We can't actually submit it without the GPS info, right?
Yeah, we could.
We could, but it's iffy. And then the GPS info lets us know if the occultation is occurring when it is supposed to occur. So
And also the geographic location.
yeah, I'm sure that too.
Can you tell if an asteroid is tumbling and the rate of spin or turn?
No, not really. Just because like it's everything's so far away, and when we run things really fast. And so normally, like if the conditions are right and the asteroid is kind of bright, you can kind of see the asteroid just get closer and closer and closer and closer to the star. But we don't have anything that high quality to actually see it, tumbling towards the star, unfortunately. That would be really cool.
But some of these asteroids have moons that Kevin
Yeah.
showed before they have.
Yeah, I'm sure
they have
Kevin's going to
rings.
talk about his beloved Adelheid.
They have
Aldehyde.
rings and moons, two moons sometimes, plural,
Yeah.
or more. Yeah, that's amazing.
These cameras are high-speed cameras, right? They have a
Yeah.
flame rate.
Yeah, I think most times when we do them here at Westport, we run them at like half of a second or a fourth of a second. Half a second's too.
No,
No, yeah, we do like a fourth of a second or an eighth of a second. Yeah, so they run pretty quickly.
Generally, how far away are these asteroids that you're studying?
Well, if you were paying attention to the first part of the presentation, Kevin explained that these asteroids are in the asteroid belt and they can also be TNOs.
Which asteroid belt? The main one?
They can be in the asteroid belt, they can be in the Kuiper belt, they can be past Neptune, they can be TNOs. They're all within our solar system though, so pretty much.
The ones that are like 200 AU out, those are still in the solar system?
Yeah, yeah. I mean, it would be pretty hard to observe asteroids and other solar systems with all the dust and the.
But that wasn't necessary, but.
Okay. This isn't necessary. This is an interaction.
That's a pretty good question. I mean, you couldn't do this outside of
I
our solar system.
I mean, I'm not the professor here.
You wouldn't have a background star.
Yeah, and then I would also think like the gas from the galaxies and the debris and all of that would obscure anything,
Maybe,
Yeah.
but certainly you gotta have a star for it to move in front of.
Looks like Kevin's itching to say something.
No, I'm just.
Yeah, okay.
Are you done?
Is that it? Oh, one more question.
Use galaxies as backdrops instead of stars?
No. How do what?
Yes, you could.
You could?
Yeah, we could, yeah.
Yeah, so then why don't you take
Kind of
this
fuzzy
question,
data,
Kevin?
just gradually.
Yeah,
Good question.
so then maybe you
We
answer
haven't.
it, Kevin.
How about that? We have.
We haven't. I guess good.
Thank you, Monica. All right, that was actually really good.
Sometimes you get lucky.
So.
Stop clocks right twice a day.
Next up is Serena, who's going to tell us about how the predictions are or how we choose the events we choose to look at. This is a little more technical, but she's got it.
Right on.
All right. So there are a few main criteria, a few main purposes, a few main things we have to achieve when we're deciding which occultations to go over. First of all, we need the time of the occultation to be at night so that it's dark enough so that our camera can capture the star's light and see it dim. Second of all, the weather, which we usually check closer to the date. We need to make sure that the sky isn't too cloudy and that the weather isn't rainy or snowing, or otherwise our view will once again be blocked. The third criteria, and probably the most limiting one, is the location of the asteroid shadow. In the diagram that Monica showed, the estimate of the occultation shadow was relatively wide for them, but it's usually rather specific, and it's best to be in the center of the edges of where the occultation shadow will be, although if there are other people and you are collaborating on it, it's okay to be on the edge. Which brings me to the fourth point, collaboration. If a lot of scientists are looking at the occultation and capturing it, even if you're not expecting to get the occultation and you're on the edge and perhaps somewhere about here, it's still useful to get it because you can narrow down the occultation, the asteroid's shape and its perimeter here. And you can still submit the data. So one of the softwares we use to identify occultations we want to capture is Occult 4.0. It has a lot of data on occultations' existing positions, which we update every time before we create our personal feeds. We create personal feeds so we can specifically tailor what we want, the size of the asteroids, the magnitude of the star in them, and into Occult 4.0, we can put our site location, so we can get occultations that specifically apply to our location, which helps reach some of the criteria. When we create a feed, we can control our search inputs, for example, the dates that the occultations will be on, the star catalog, the magnitude drop, the duration of the occultation, and we can save the file. The initial search outputs look like the ones on the right, and it takes several hours for this to run because it goes through hundreds of thousands of asteroids. When we save the data, we save it as a CSV file from JPL Horizons, and we rerun the data with Jet Propulsion Laboratory just for nearby occultations. We do this because the Jet Propulsion Laboratory's data is more accurate, but it takes a much longer time to run, so we can't do it with all of the asteroids we want to. We then save these events to Occult Watcher. Occult Watcher is where we view the final data on all of the occultations and the ones that are usually more relevant to our location and everything. We can choose our prediction feeds. We always choose personal predictions, which are the ones that we've created for our location, in addition to some of the more general global feeds. And Occult Watcher, which also has our location, can predict the probability that we're going to get an event based on where we are and where the occultation shadow is predicted to land. We can sort the occultation lists based on the probability we're going to get it or the date, which can make it really easy to find and see the data for occultations on here. In addition, on the Occult Watcher website, we can announce that we're going to analyze an occultation, as you can see with those two telescope logos, two telescope icons, where they each represent a different site capturing the occultation, which is important because, as I mentioned earlier, you're more likely to want to submit the data for the occultation if there's other scientists working on it, because you can compare that data, which is helpful for figuring out the asteroid's perimeter.
Serena, who else is doing this? It's the New Milford group or?
Here?
Talk about that.
Oh, you, okay. All right. Good question. Don't want to bury the lead here.
And lastly, a new update on the Occult Watcher website is that you can, without downloading the software or creating a personal feed, you can go to the website, create your own filter by adding your location, as I did above, and search for any date and find all the occultations for that day. And once again, you could go on through that website, you could announce that you're going to do it once you decided that you want to capture that occultation. Are there any questions?
How many of these do you get a month or a week?
Occultations, there are a lot of possible ones we can do, but we get clouded out by a lot of them. And some of them are either too low probability, so we decide not to do them, or they're at an inconvenient time. I'd say we do a couple per week if the weather is clear.
What are your cutoffs? Like with how low on the horizon? Anything above 10 degrees or higher, or where do you?
Probably about that, yeah.
And do you always use this GPS location?
Monica and I usually go here. Kevin and Sangeeta and other students sometimes go to the New Milford or New Haven locations. We have a few.
The best location is Westport, obviously.
Yes.
The easiest one.
I didn't like say that.
Yeah, it's debatable.
Are there any other questions? Okay, thank you.
So, just a quick ending to that, the Occult Watcher, there's the program Occult Watcher, and it's all moving to the cloud, the Occult Watcher cloud program now. You can actually go, it's occultwatcher.net. You can go there, put in your latitude, longitude. It will tell you it will give you a good set of asteroids you can look at. It's the technology's come way up these days. It used to be a lot harder to find events, but
Well, I remember back in the day here,
a lot.
they
easier.
we would get like this mail from Tom. I mean, they would send us like this circled sheet, a printout sheet of the stuff, like once a month, and it would do this huge printout sheet of all the asteroids that maybe you might see from here.
Yes,
maybe.
Yes, it's
It was, I mean, it was
a lot-
ooh,
it's a
dude.
lot nicer now.
Bob did that. Who did that? No, we were. When I was doing it, we were using a cult watcher. It was on the computer.
Well,
Computer gave you a list of your location.
that's true. It used to be before that though, there used to be this publication called Tonight's Asteroids where it would give a list of asteroids you could see, and it was usually 2 or 3 months ahead, and there'd be
Right.
like 5 or 6 asteroids.
That's what I saw.
And now you could actually do, again, what Serena said is correct. It's how convenient the time is to see these things. They happen all night. And there are some at 3 in.the morning, which we haven't been doing a lot of those, but it could be done. So anyway, going on, I'm next going to pass it to Sangeeta. And Oliver, are you also helping? I don't know, as you wish. And so Sangeeta and Oliver are up at the McCarthy Observatory up in New Milford. And they have also recently started also doing occultations in conjunction and separate from what we've been doing here. And so let me pass it to them, and then I'll go on. I'll talk about New Haven and then where this thing's going.
Just a quick question. Are any of the stars large enough to have a partial occlusion?
There's so for instance, Betelgeuse, there was a recent occultation observed of Betelgeuse. Betelgeuse is the,
Don't say 3 times.
oh, that's twice, isn't it? I better not say it a third time.
Is that going to happen soon?
So what, the explosion of
Yeah.
the star that shall not be named? Yeah. Oh, that's a really good question. But there was an occultation of it by a smaller asteroid, and the asteroid did not cover the entire star. Yeah, so it depends. So most of the stars are far enough away, and the asteroids are big enough that that's not an issue. But yeah, you can have partial dimming of the star. That was down in Florida. I considered going there, but it was a bad weekend. I think I didn't.
That counts as an occultation though, right?
Oh, it's
See the dim.
definitely, yeah, yeah. Is it technically an occultation? That's a good question. There's another name for it.
Partial eclipse.
Yeah,
It really is.
there's another name for it too, but I'm trying to think what it is. It doesn't matter. Okay. So let me just introduce these two. Sangeeta, I had it. Cultibola, yes. Recent UConn grad. She's applying to grad school, and so she's doing this during a gap year. And Oliver Outwater here is he's come all the way from Litchfield, is it?
Yep.
Yeah.
Oh,
And so that's a bit of a drive. And so he's these two have been taking up the mantle at McCarthy, who is now the whole team up there is very interested in doing occultations, and particularly in conjunction with us, so that we're, more is better in this case. It's all yours.
Thank you. Hello, everyone. I'm Sangeeta. Again. So we're going to talk about observations at JGMO. I included this GIF of the main belt asteroids that Kevin was talking about, but I think mine is a little bit cooler. It's moving.
100%.
But,
Yeah.
Mhm.
I'm not seeing speaker notes here.
Oh, I
How do I see my notes?
I don't know.
Oh, just wing it.
Yeah, just go for it.
All
You
right,
got it.
well, I'll give you all a brief history of the JJMO and why it's important. So the John J. McCarthy Observatory was kind of like a start to the millennia, I guess. So they built it in New Milford at the high school.
On the football field.
Yep,
Yeah.
on the football field, actually. So it gets really drowned out by the lights.
Yeah.
They have a super nice telescope, actually, a 17-inch plane wave. The optics are great on it. And they have a warm room right next to the main room. So it's not like here where you have to go all the way down the 2 stories to be warm. You can just sit in the warm room the entire time.
Oh, yeah. Yeah, and they have like the computers there too.
Yeah, yeah, we have computers, everything in the warm room.
Mhm.
And so why it's important to have the I guess outpost at JJMO is so we can just get more data. So all of our current stations, I guess, down here are all at like similar latitude. We don't really have anything as north as JJMO. So we can kind of triangulate, I guess, the object better than we would if there was only WAS and New Haven and Greenwich sometimes.
Sometimes we also see like different events too, because like it
Yeah.
depends on where the asteroid is traveling, like the path and the shadow. So sometimes it can be only seen in New Milford versus Westport, or sometimes it can be seen in both. So,
How narrow are those shadows? They're very narrow, or it could be very wide. couldn't
yeah,
they?
I guess.
They're the size of the asteroid.
Yeah, the size of the
Yeah.
Well, it
asteroid.
also depends on how close the asteroid is to us.
Mhm.
Doesn't-
Well, they're all pretty far enough away that
Yeah.
it's basically the size of the.
Yeah, I
Really?
mean,
Okay.
a lot of the shadows are kind of like half the width, I guess, of Connecticut. I feel like that's kind of like average.
Yeah, I feel
You
like
think?
a lot of occultation events that we have observed are seen at both Westport and New Milford. And
Yeah.
if you look at a map, I'm not good at geography, but if you look at a map, you can understand how big you can kind of see it between both areas.
You have some shown.
Oh yeah, I do. Okay, yes.
Oh, yeah.
Yeah, so I was gonna talk a little bit about some notable events that we've observed at JJMO. So we've recorded over 10 events at JJMO. This is not including like when we got clouded out or we just simply missed it. This is just like notable events. And this is like the path I was talking about. This is 3 that I focused on because I thought they were cool. But so this is the actual like asteroid path, and this is like the area of like error that we talk about, and then the yellow lines between all of them are where we observed it in New Milford. So I guess in like some areas you could see that we observed it in like New Haven and New Milford, and then some are in Westport too. But then some are like specific to just like our area, so we can only observe it, as you can see here, only in New Milford, and not the other 2 sites. So yeah, so these are some asteroid occultation events that we have observed. These 2, Spellman and Palisano, are main belt events, but this one, the TNO, was yeah, it's a TNO. So meaning it wasn't part of the main belt, is in the orbit near Neptune. And this was a huge diameter compared to these 2. This was like 331 kilometers, which was huge. Unfortunately, all of these were misses, but as you said before, misses are still significant. They're important, which is why I've included them, because good data, right? All like bad news is still news, you know. But we did get a success. This is back in November, mid-November.
Oh, it's an interesting day. It's like an important day.
No, I don't know what happened on this. I don't know, but this is
Your birthday?
oh wait. I'm sorry.
She reminds everybody of her birthday, like. any
This
event.
is a birthday occultation.
That's only 10 days for Monica's.
Yeah, but this is in New Milford, and this is where we observed, and this is also in Westport. They observed it there, but I don't think Monica was there because
my birthday.
yeah, she was celebrating her birthday. She was celebrating her birthday. So this was like the manual recording that we did of the data, but we also analyzed it via a software, PyMovie. And so this is the light curve that we had. So this is the general light curve. We usually do our occultation events over like 4 minutes, and then in the middle of that is where the dip you should see. So this one, since it's a successful event, this was the dip that we observed. It's a little bit below 0, so we know it was a hit. And I also included this cool GIF that would explain it well, because if you see it successfully, like on the the software, like when you're actually doing it at the time of event, you should essentially see that the star is dimming, because that's when the asteroid is occulting and passing by it. And so it'll dim. So it'd be the the DNR, the disappearance, and then the reappearance. So that's when the dip would happen. The dip would happen when it disappears, and that's what we see here too. So yeah, that would be a successful event. Hopefully we get more as we go on and do more occultation events.
What are the other spikes on there before and after the
Noise.
Noise,
Yeah.
yeah, just noise, yeah, from like background.
That's just atmosphere bouncing around.
Yeah, you can see
Yeah.
that the other stars will also have the same pattern.
Oh, yeah.
So that dip in the
Oh, yeah.
first part there, you see that also with the nearby, the other stars in the field. Everything kind of goes down. Yeah.
Can you go back two slides
Yes.
to the?
Sorry, I put translations.
There, okay.
Yes.
Now, how did you determine that line that went through Long Island?
Which one? Oh, this one?
Yeah,
Oh, I don't know. Is that like an error?
That's a different, that's another observer.
Yeah, yeah. Yeah, so yeah,
Down
so
in, Pennsylvania.
yeah. I like zoomed this on our
Oh.
area, but this is actually, this specific one at least was observed like worldwide. So I zoomed in on this specific area, but there's places all around US, in Europe. So I think that's why you can't see all of them and you can't see that shadow that you would have seen, but
Each
It's just
person
specific.
gets their own like line, I guess. if
yeah.
you're Observing on the map.
And that's if, like, one of the things that that Monica had in her presentation, she had 2 asteroids that had lots and lots of lines going through it. The more lines that you have going through it is the more people looking at it. And the more
Yeah.
people look at it, then you can see the size and the shape,
Yeah.
and you can see actual details of the asteroid.
Yeah. 'Cause
But you know, when you just have like 1 or 2 chords going through, you just kind of just see a little bit.
yeah. Yeah.
When you're predicting those lines, is our sun have enough mass that you have to take
into account the bending of the light?
I'll take this.
Okay.
The answer is yes. And it's even more bizarre than that. So the bending of the light occurs because of the mass of the sun warps space. And so the light from the star gets hurt. But the asteroid is not as far away as the star. Its light is also bent, but not as much. And so it's even more complicated than that. You have to do the full bending for the star, but it's only a partial bending from the light from the asteroid. Does that make sense? The position of the asteroid. It's a lot more complicated than you would think, but those calculations actually go into the prediction. And if you don't include that calculation, the general relativistic correction, you can be off by 5-10 kilometers. It's that big of an effect. So the
That's a
shadow
lot,
would move
much more
by
than
5-10 kilometers.
It's a lot.
That's a lot. Yeah.
That's a good question.
Yes.
You want the question on?
Yeah.
Can you explain a little bit about the specifics of the paths? So they always seem to go in the same general direction, but obviously they're not always the same because of the location of the asteroid in its general orbit, like on the earlier slides that Kevin showed. But what are the different things aside from their relative positioning in that orbit that are changing the direction of that line? Like, does it always have, it seems like in some of these pictures, the slope is a little steeper, but the path is generally the same. And how,
I guess it's just because of the location of it, right?
Well,
Yeah.
it's the location that has to do with the orbit of the asteroid, which path it's moving relative to the Earth. It can be,
Just how everything rotates.
it could
I
be,
guess.
yeah, it's,
Kind of.
it can be.
Plane, like an XY plane, it's kind of like it could differ on the plane or XYZ plane, I guess. But it would differ on the plane, so that would also differentiate whether it's orbiting this way versus like this way.
Earth's rotation affects it too,
Yeah.
and how fast
Does
it's
that answer your
moving.
question?
Yeah.
so then my
other question is, what would be the optimal spacing if you were ever really excited about getting the best data on an asteroid and you had either, 3 or 6 outposts? Would you want to be, as wide as possible within the shadow range, or would you want to just, because you don't want to be too close? I get that part, because if you're too close, then you're kind of just getting the same thing, right?
Probably
I
equal,
guess the
equal distance from each other.
So that would depend on the size of the asteroid.
Yeah.
On the big ones, you can be spread further apart. Let me answer that question in the later slide.
Yeah. Okay.
Nicole asking the tough question.
Yeah.
Is that it?
Yeah.
All right.
Oh, good job, guys.
Thank you.
Yeah, and having New Milford join has been, it's been great. Of course, I get less sleep because of it, but, it's been great. So some of these things we've already discussed. Let me just do this quickly. I know we're going late. That's good. A lot of questions. Let me just, I'm having a senior moment here. Just give me a second here. Yeah, senior moment. All right. So what button do I push? All right. So as before, the occultations tell you about the size, shapes, and orbits of the asteroids. It can also maybe detect binary asteroids, moons of asteroids. There have been some occultations showing rings of asteroids. There are a couple of asteroids that actually have a ring of dust around them, which is kind of amazing. And the other thing you can do is you can probe star systems. So some double star systems have been discovered via occultation. So this is, in terms of a moon, this is one that we have evidence for from an occultation back in August of 22. This is Adelheid. This is now my favorite asteroid. And so this is the main light curve for the main body. It's a big asteroid. It's about 120 kilometers in diameter. And then shortly after, there's this little blip that occurs after, which is best described by having a moon in orbit around this asteroid. And that's about 300 kilometers distance between the main asteroid and the moon candidate. So there was another observer in Arizona who was also observing this. He was right, very close, but he did not see any evidence for a moon. So the question is, what's this? There needs to be a follow-up. There's in terms of verifying or confirming the detection of this moon. But that little moonlet there would be about 8 kilometers in diameter versus the 120 kilometers in diameter. But the distance here is like 300, 400 kilometers distant. So to answer what kind is the optimal spacing, to see this again, the optimal spacing would be about every 6 kilometers over 600 kilometers. So you would want 100 telescopes to be able to definitely make sure that you see this thing in a confirmation. Yeah.
Kevin, with the moon, since you're the only one that saw that, is there a chance that it could have been just a bird flying overhead?
Now the bird won't do it. That's a good question. The bird would affect the entire star field, and that has to do with the wave nature of light. A bird won't do it. And then you have to have something that would be very specific to that area of the field, because you're taking a whole bunch of, you're taking an image of the entire field, and there are other stars there. And this is the only one that dips. And not only does it dip, but it dips all the way down to the same level, so that it disappears. The star disappears completely. You would not see that with the bird in that case. So plane would do the same thing as a bird, would really actually be worse. I've seen planes go through the field and they have lights, and so the lights really
Right.
are
Can't miss that.
are an issue. Contrails could also be an issue. That tends to dim the entire field. Satellites would be in bright, you see them, right? Yeah. What? Superman? I hadn't thought of that one. All right. So is there another shot for Adelheid? Well, how about let's go to Prince Edward Island in March, maybe?
Ooh, tough place. Yeah.
Huh? No, I'm not going there. But anyway, that would be the next one. And then there's one other. There's actually one in September 26th down in the Carolinas. And so, if we could get 100 telescopes here, we could maybe find that moon. but we need 100 telescopes.
So would that be the green moon if you do discover that? Is that
I would have naming rights, yes.
really, you would?
Yeah.
Wow.
You detect. Now, here's another one, by the way. This was the event right after Adelheid. It's amazing. This, for some reason, is not considered as good as the Adelheid event, but this was another one that came through in October. And then here's the main dip, and then there's this guy right there that's just before it, and that to me looks like a potential moon. I forget when the next one of this is. This is a hard thing to see. It's a small asteroid, but there it is.
What's the time frame? How quick did that happen?
Oh, that's a good question. Let's see. The 0.6 seconds was the predicted main body, so I think that's about 0.6 seconds. And so you're running the camera pretty fast.
To get that moon too, then
that,
that's a
and you can't,
tenth of a second.
yeah, so you can't get the count, the faster you run the camera, the less light you get, so it's just statistically less significant. All sorts of issues related to that. There are other things we've done. This is Titania, the moon of Uranus, and one of these lines is ours, line 18. Let me just put my glasses on. So that's down in here. We were able to detect one of those. We actually got the position of the moon to a much higher accuracy. It was supposed to be here, and actually the center's down here. So the moon was off by, that's probably 100 kilometers or so. So that's the kind of improvement that you can get of the solar system bodies.
Certainly important if you're trying to send a spaceship there and
Yes.
you don't want to go splat off the
Yes.
moon.
So JPL is very interested in all of these observations. This is one of the, I pointed this out earlier on that scatter plot. This is that distant object that's beyond the Kuiper belt, beyond Pluto. And there are two lines here, and I'm sorry to disappoint you, Monica, but there was someone else who was helping at the time, and this was Christine Gao. And so she was actually helping on one of these lines is ours. I forget which one it is, but this is object beyond Neptune, 630 kilometers by 470 kilometers. I don't think this made it a dwarf planet. This is not, I think it's considered sub-dwarf planet size. Doesn't seem right though, does it? Anyway, we were the first ones to measure get a nice, good, concise, relatively good measurement of the size of this object that's way out.
So we got two measurements on the same object?
Well, the other guy was in Spain.
Oh.
The other guy was in Spain. And this was one of those that was, I think it was a 2% probability.
Whoa.
So to get it, and we got it. So, there's kind of a strategy. You have to have a strategy of these things. You don't want to get up at 3 a.m. just to see a 2% probability event, right?
Now you have your assistant.
That's right. That's what Monica is for. Yeah.
Yeah.
All right.
That's
This is one that Monica did. And that was the predicted path for that one. I'm just showing a couple others. This is one of the most recent ones where we had it was heartbreaking. Arecibo is the asteroid. And so Rick Bria had two telescopes in Greenwich on it. Serena was in Westport. We put an we tried an automated station at a new site. This is the New Pond Farm in Reading. They have a telescope system there, and they've wanted to join, but they have an issue with they need the adult volunteer to help oversee what's going on with the students. And so we just decided, well, hey, how about we put an automated telescope there. We'll just put it there and then we'll run it remotely. And they said, yeah, that'll work. So we tried that and unfortunately it failed. It was a power issue. The power in the laptop was plugged in, but I think when we moved it into the cover, it dislodged and we lost power on the computer, and so we lost that. And then the fourth telescope was at New Milford clouded out. Unfortunately, that was a 3 a.m. event.
It was like 4:43.
Was it 4:43?
Yuck.
Yeah, anyway, Greenwich clouded out. Westport was clear. Serena got this thing.
All right, Serena.
Unfortunately, I don't have that observations. Why were we so interested in all the stations? I mean, we're interested for all the reasons that you've learned about, but Arecibo is known to have a moon. It was the first one that you could say it was definitively, the moon was definitively found by occultations. And so this was the original discovery where there were two people relatively close to each other, found a dip from the main body and then a second dip from the moon. And then that was followed up by an observation a month later. A similar thing happened. And so we would have been, had all the stations not been clouded out or worked, I think we would have been the fifth detection of both the main body and the moon, which it's at the stage now where the orbit's getting pretty well known of what the moon is. And the great thing about the moons is you can use Newtonian mechanics to figure out then what the masses are of the two systems. You know now the size of the two systems, that gives you the density of these rocks, and the density then tells you what it is, in essence. Yeah.
Question. This may sound borderline idiotic because a lot of this is going over my head, but I'm wondering, like with the Adelheid occultation, so for the future events, will that be including like a different star, or is it? Yes. Okay.
Yes. I don't know if there's ever been an occultation of the same star twice.
Boy, that's got to be rare. The trillion stars up there. Yeah.
Of the ones that have been observed globally so far, I don't know if there's a repeat. I looked once and there wasn't one maybe 2-3 years ago. So yeah, that's a good question. All right, so where are we going with this stuff? Recently, there is the Gaia satellite, which has measured the positions of the stars and 10% of the asteroids to very high precision. So we know basically where a lot of the big asteroids in particular are going to be, where those shadows are. And so the shift is getting from the single cores to going to multiple cores, which is why we're trying to bring in, you know, the McCarthy Observatory, and we're bringing in University of New Haven, and we're trying to get more telescopes up so we can do more of these chords. So that's the first thing. Moons are if you can detect a moon, that's really good science. That's high value science if you can do that. And then there's a lot of interest in these things that are way out there, the TNOs and the Centaurs. There's also the potentially hazardous objects. So this was actually, you can't see from the map very well. This is the Cape. And so here's New Bedford. This is Rhode Island is here.
They got Martha's Vineyard, so everybody.
Yeah, this Martha's Vineyard. Yeah, there you go. And right there it says it, Martha's Vineyard. And so this was last night. We could have gone to the Cape, the Cape, and actually observe this thing. Yeah.
Do people have telescopes that?
Do people have telescopes that can travel but also still do this, or do you really need something the size of the community telescope?
Oh yeah.
That's a really good question. Let me show you. So we want multiple stations. We also want to automate. This is the New Haven telescope. It's a 12-inch telescope. It's got a go-to on it, and we almost have it automated. We have it so that we can remotely access it. If you're near a Wi-Fi, you just tie into the Wi-Fi and then you run it. remotely. So, and this is New Haven. This is one of the nights we were trying to observe, and this is the direction we were trying to observe.
Look at that. Right.
And, a lot of people out on those tennis courts at this time. Go figure. So the answer is yes. I mean, this system is roughly, if put all in, it's probably about $5,000 to buy one of these systems for this size. And you can do it cheaper, a smaller telescope. You can do a little cheaper, but I think this is like kind of optimal type of a setup, and you can take this anywhere.
How
Part of
long
the
is,
issue with Connecticut, though, is you can't go anywhere because you sit down and 20 minutes later, there's a police car that's going to be there asking you to move your, because it just, you have to get approval ahead of time. This is what I've discovered. Oh, can they be checked?
If somebody is flying somewhere.
that's pretty big, isn't it?
We were just in the desert.
Would have been amazing to have had something like that with us.
Yeah, you'd have to get a traveling case for the stuff. I don't know about the bottom piece, the mount piece. That I don't know. I haven't seen a
Be
case
tough.
for those.
That'd
You
be
get a
tough.
case for the tube. There are telescopes where you can do that. We have one over here. There's a 10-inch, not that one. It's in a case
This
somewhere.
black case back here.
Yeah, so you could do that.
That's definitely, that's a portable, that's, everything is in there except for the tripod though.
Yeah.
So the tripod, I mean, you could get that pretty well beat up on a plane.
Yes.
So that's,
Proud with your efforts to automate that telescope from down here,
Well,
because I was shocked to see that.
so I was hoping to actually give you a live demo tonight, but unfortunately it's cloudy, so we can't really do that.
Like a regular occultation.
But yeah. But yes, we are, so we can, if you can set the camera up upstairs and then tie into it via it's Google, what's it called? Remote. TeamViewer works, but just the remote access via the Google, the Chrome interface, it works just as well. So I have set that up there and then come down to the warm room and actually control the telescope from the warm room, not having to go up there. And then the next space, which is what we can do with this guy, which is really great. There's the plate solving software. You point it to a part of the sky, you take a picture, you send that picture to this plate solver. The plate solver then tells you exactly where the telescope's pointing. So you're done, right? You get close to where you think you are, where the star is supposed to be. You take a picture. If you're off, it tells you you're off, and you remove it, and you get right on target. This is part of the automation process. So the procedure then is you go to the star, you plate solve, you reset it so that you know you're on target, and then you just wait for the time of the event. You take the event, you go to the next one. You can now do 5, 10, 15 occultations all night. 2% probabilities, 3% probabilities. The telescope doesn't care, right? And then you can come back in the morning or on the cloudy nights, and you can go through the events and look at the events.
how long is the setup on that scope? Is it, 15, 20
We
minutes
got it
longer?
down to 20 minutes, yeah.
Good, yeah.
20 minutes. So, yeah, we're getting there. We're getting there. I think this is the future. Automated scopes,
You've been working towards it for a long time
a
now.
very long time. The best thing is that there are people who are now helping do this with multiple cords. And so that's really where we want to go next. And I think that's a good place to stop.
Couple questions.
Yes.
Question from the online audience. One asked, Rick Bria asked, what mount are you using at JGMO?
Oh, that's the plane wave. Well, that's the plane wave. It's a 17-inch plane wave scope. They have invested a good deal of money up to the McCarthy Telescope up in New Milford. I recommend people just go see it. They've leaped ahead of us, guys. I think we're behind the curve. We gotta catch up here.
We need a good grant.
We need a good, like $80,000-$90,000 grant.
Yep.
Yeah. Yeah.
Another question is, if there's a commercial application of a star, does that make the data less reliable or more difficult to use for research?
It takes a little more analysis, but it's just as good. It's just as good. Yeah. Yes.
Just wondering, having heard about asteroids that have base and precious metals in them, you mentioned that you can measure the density and size. So can we infer like what's actually inside them?
If you get a density that's greater than 3 or 4, you've got something interesting there. 3 or 4 grams per cubic centimeter, you've got something interesting. Most of these asteroids are the smaller ones are called rubble piles. They're basically collections of small rocks that have come together
Gently.
Gently, yeah. And so the density of those are actually less than 1 gram per cubic centimeter. If you were to put it in a tub of water, it would the water would be absorbed by this thing because it's mainly just empty space. A lot of it's empty space. So yeah, if you got a density of, relatively strong, like 3-4 grams or higher, you have something.
Yeah, but I must have missed that. Where are you checking the density of these asteroids?
Well, okay, so the density would then come from a double star or double system with a moon, okay? And
of course, right.
yeah, you have the size of the thing, and then the moon tells you the mass. The moon, the orbit of the moon, would tell you what the mass of the 2 objects are.
Right.
So from the mass and the size, you then will get the density.
So normally you couldn't tell as long as if you don't have a moon.
If you don't have, no, you
Right.
wouldn't. For a single asteroid by itself, you would not be able to determine the density.
Got it.
Yeah. You can make an estimate based on the size and,
Its orbit, probably.
yeah. Well, no, I don't know. That's a good question. You wouldn't have it. You wouldn't have a density. Yes.
Yeah, I just, maybe this is a little tangent, but you did show us a slide in which there were potentially dangerous asteroids. Okay, so I was wondering about that in terms of, is that where they're trying to shoot them down or something like that?
Well, yeah, so there's the DART mission that was
She's speaking with us again in March, Frank, in April.
so the DART mission is where we sent a satellite into the moon of another asteroid to try and change the orbit.
Yeah.
And it
Something like
did.
that. And okay, now what was your question exactly again?
Well, if are those potentially hazardous ones, the ones that they're trying to shoot down?
Cannot shoot down a 100-meter asteroid. We don't have the technology to do that. Well, it's only at Hollywood do we have that kind of technology.
The thing,
Identifying them.
Yeah, this is all
Worry about it later.
what we're doing right
Right.
now is we're it was in the mid-90s, Congress allocated money to to find and quantify the risk of the asteroids. And this is when the movies came out. What was it? Armageddon with Bruce Willis and
remember too,
Deep Impact.
that even if you blow something up, you haven't changed the mass.
You have the debris. still.
Right, and it's all still coming at you. It's all going in the same direction.
so-
Now you just have 1,000 million pieces of it instead of
So,
one.
Yeah, this still represents a threat to humanity. These potentially hazardous asteroids. Now, most of these newer ones, I have to say, most of those are small. Most of those would burn up in the atmosphere. So those would be less potentially hazardous. I put that in the heading here, which I now realize is wrong. Notice it says near Earth asteroids. So many of these are near Earth, not hazardous. The bigger ones here, 100 meters or greater, hazardous. In 2015, there was the Chelyabinsk meteor that went through I want to say, was that 60-meter diameter?
I think that's about right. Yeah.
Yeah, it's about a 60-meter diameter. No one died, but there was a lot of damage from the shockwave that came off of that thing in Russia.
How big was the one that hit, that went into Siberia, you know?
That's it. That's Chelyabinsk.
And how big was it?
That's a really good question.
Well, I think it was about 60 meters.
Probably. There's no crater for that thing.
Well, most of it landed in the water.
It was an airburst, so it was probably ice or whatever is what they think. There was no, that's a really good, that's a
But it
good
landed
question.
in a lake.
But it was huge.
Yeah.
I don't
There's-
know. I don't know the answer to that.
Pattern of the trees, the way it blew down, it came in at an angle about 30 degrees. So.
Yes.
I have two more questions. My first question is, do you daydream about what you're gonna name the moon? No?
No.
You gotta let me name that.
So name of
He actually does.
the main body is called Adelheid. Adelheid is it's a German, I think, feminine name is basically. So if I were given the opportunity, I would try and match it with Adelheid, but I would have
Edelweiss. Edelweiss.
so. But no. My goal, I tell you, I would love to have an asteroid named after me, but I'd like it way out there so that no one ever touches it for a very long time. And I'd like 2 moons around it for my 2 kids, and I would name the 2.
There it is.
the 2
That's a
moons.
good way to end this
How's
one.
that?
Oh, hold on. I just forgot it for a second. Oh, yes. Okay. So, with your training and the fact that you're constantly doing these occultations, you know a lot about what the asteroids that you're doing the occultation on as it's coming. Is there a tremendous amount of curiosity for people that are doing these as to what the data captured gets used for in the future after the fact? And because of you're a professional, do you already sort of know how it's going to be used and it's just not that interesting? Or is it kind of like publications? I'm in the biology field. So like for me, it would be very interesting then to see where the publications were sourced years down the road and what it contributed to in science.
Science goes through phases, there's certain things get topical or not. The main topical one now would be the potentially hazardous ones. Those are probably the most valuable in terms of occultation data. And then the other side is beyond Neptune. A lot of researchers are more interested in those. I have this funny thing that I'd rather get the main belt very well described, knowing all of the sizes and shapes of the things in the main belt so that we would have a good estimate of the mass of the main belt. It turns out that the orbit of Mars, there's some discrepancies in the orbit of Mars. This is not well known, this type of thing. And so the question is, well, why is that? And most people point to the asteroid belt. And so, I would love to get the main belt nailed down better, but to do that, really, it's a array of these things across a much larger swath than we have here. This is just kind of, can you do this? And I think the answer is you can do it. Now it's a question of scale. Yeah, what this group has done is show that it can be done. It's
Good
great.
job putting it together. And, because that was one of the first things when Kevin came here that he wanted to do. And we're just like, okay, great, we'll try, and, but, it took quite a few years for it to kind of come together like this,
Yeah.
to get people that were going to do it and that consistently. And now you're growing it. So that's really well done.
Yeah.
Really well done.
A cult leader? I'm the occult leader. I'm the occult leader. Okay, I'll take it. All right.
Nice job, Kev.
Thanks, guys. And thank you to the students here, the 4 guys did a lot. All right.